Hello friends, I am Dr. Sanjay Gaikwad from BJS College, Wahuli. Today we are talking about the bonding in solids and electronic properties. It includes the crystalline solid, unit cell, type of unit cell, bonding in solids, free electron theory and electron conductivity. Then we are talking about the bonding in solids with the help of molecular orbital theory, simple metals. Then semiconductors like silicon and germanium, its property like photoconductivity, the P type of junction, PN junction, field effect transistors, bands in compounds like gallium arsenide and bands in D block compounds like truncheon metal monoxides. A crystal or crystalline solid is a solid material whose constituents such as atoms, molecules or ions are arranged in a highly ordered microscopic structure forming a crystal lattice that extends in all directions. That means when crystals are formed, the first atom joined to the another atom and then third atom is connected with the lattice and it forms the perfect geometry. Then we are saying that in all directions, then we are saying that it is a crystal. The crystal lattice and unit cell crystal lattice is the depiction of their dimensional arrangements of constituent particles like atom, molecules, ions of crystalline solid as a point, or the geometric arrangement of the constitution particle of crystalline solid as a point in a space is called as crystal lattice. Means it having the each and every atom joined together in a perfect manner. Now when we are seeing that this perfect manner, we are taking the small unit that is called as unit cell. Unit cell we can define as the unit cell. The simplest repeating unit in a crystal is called as unit cell. Each unit cell is defined in terms of all lattice points, the points in a space about which the particles are free to vibrate in a crystal. Now in this case, for example, the crystal having the length A, B, C length and with angle the alpha, beta and gamma, then unit cell is characterized by these six parameters and we can observe number of such type of crystals. Now this is the first crystal where we can identify what type of, suppose 4 are at the cube and at the cube is divided into the 8 part, and when we arrange all these cubes, atoms, then we observe that in the first only one particle present in the per cube. Now we can identify in terms of the body centered cubic cell. Now we observe that 8 atoms at the end and 1 atom in the center. And if we cut it all these cubic parameter and the corner atom get divided in 8 part is divided in the 1 cube, and then we observe that if we count all these parts, then it is observed that there must be only 2 atoms are present in the cubic center. Then body centered cubic cell having the 2 atoms, and if we understand the face centered cubic center unit cell, then we observe that 8 at the corner and 6 faces are there. At the 6 faces, 6 atoms are there. 50% of the atom at the face in the cube, and such a type of 6 atoms are there. Therefore, half part of the each atom, and at the corner 1/8 part. Then we count all these atoms. Then it is observed that from the corner we observe the 1 atom and 3 atoms are there from the 6 particles. In this way, face-centered cubic having the 4 atoms are there. Now such a type of unit cells, in case of the first unit cell where we observe that at the corner, only corner at the 1/8 part, therefore 1 atom is there. In the body centered, 1 atom at the corner and 1 at the center, that is 2 atoms. And here the 3 atoms at the face and 1 atom at the corner. In this way, the 3 plus 1, 4 atoms are included, where less space is available as compared to the body centered as compared to the simple cubic. Now in this way, the unit cells are there. Now these unit cells are again further divided into the simple cubic, tetragonal, then orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. Now according to the difference in their sides as well as difference in the angles, these 7 types are there, and each face center, body center, and simple cubic. They are classified in these three curves. Now, when we are thinking about the bonding in solids, now with respect to the free electron theory, all structures are given in the form from the net. It is available. Now, in case of the ionic compound, what happened? The sodium it donate the one electron to the chlorine and completely transfer. Therefore, charges are created and ionic bond is formed. While in case of the covalent bond, it is observed that the one electron from one atom and other electron from other atom, we get the formation of the covalent structure. In this way, covalent bond is formed. While in case of the hydrogen bonding in water, the hydrogen forms the very weak hydrogen bond with the oxygen. Such a type of bonding is also there in the liquid forms, and therefore we observe that the bonding. Now, in case of the coordinate bond, the metal forms the coordinate bond with the ligand. Suppose that, for example, nitrogen, halogen, then sulfur, phosphorus, oxygen, these type of organic moieties are present in the compound ligand. It immediately donates the pair of electron to the central metal atom and it forms the coordinate bond. While the last, that is a metallic bond, is most important for our purpose to explain this bonding in the metal. Now, in metallic bonding, what happens? The valency electrons are continuously transferred from one atom to other atom. They are tremendously with this high speed. They are moving from one atom to other atom, and therefore these metallic bonding and form these lattices, lattice structure, and the electron are very free, and it's shared by the whole lattice. These free electrons move freely throughout the lattice, and hence that we term as a electron gas, and these electrons are coming immediately, we are observing, and to get at any point. Now, in case of the electron interaction and the electron ion interaction, it appears as the electron move in the consonant box and periodic collisions with ions in the lattices. Now, the Drude and is utilized and explained the many properties of the metal, which has such as electrical conductivity, thermal conductivity, etc. And he applies the equation of simple mechanics on the electron to derive the several expression and also arrive at the Ohm's law. Naturally, the electrons are in the random motion throughout the lattice, and it helps to calculate the whatever the charge on the electron, then applied electric field, then mass of the electron, and distance from the direction of motion. It can be find out with the help of this equation. This equation is also called as a Newtonian mechanism for the Drude equation, and we can write this equation to calculate the free electrons theory. And in case of the molecular orbital theory, it also found what type of chemical bondings are there. Now, in this case, two atomic orbitals are there. The electrons are taken from the two atomic orbitals and they combine together. It forms the bonding pair, and some electrons, if remains, then they are transferred into the anti-bonding, and some they are not utilized in the bond formation. They are in the non-bonding. Now, this MO theory, molecular orbital theory, is same as like a crystal field theory, valence bond theory, as well as in case of the ligand field theory, crystal field theory. This MOT can help what type of bonding is there, whether it is a strong bonding or weak bonding, sigma bonding or pi bonding or non-bonding. Such a type of bonding can be explained with the help of MOT, and it also helps in the what type of chemical bondings are there in the solid structure. Now, these are the electron gas. Each and every electron in the metal, they are moving randomly and from one atom to other atom. Therefore, these are the good conductor of electricity. Now, in case of the semiconductor, this is the most important property of the some metals where semiconductors. It is a class of crystalline solid, intermediate, and the electrical conductivity between the conductor and insulator. The space left behind the electrons allows the covalent bond to move from one electron to another, thus appearing to be the positive charge moving through the crystal lattice. This empty space is commonly called as a hole and is similar to the an electron, but it with the positive charge. In this way, the electron moving from one place to another place, as well as hole is moving from one place to another place. Just only the holes and electrons are there opposite to each other. Now, in case of the carbon family elements like silicon, germanium, these elements having the fulfill in their electronic structure in the covalent bond, Now such a type of structure, when suppose the electrons deficient phosphorus is added, then what happen? One electron is more, and what happen? Electron sufficient phosphorus is added. The one electron is there, and this electron can jump from one place to another place. In such a type of conductors, we conduct the electricity. We are saying that it's a N type of conductor. And when boron type of elements are added into the or doped into the silicon metal, then there must be a hole, and this hole travels from one place to another place. This is the positive charge moving. This is called as a P type of conductor. Now such a type of electrons are moving from one place to another place. When the holes and electrons are moving from one place to another place, they are moving in the opposite direction, and therefore we are using this property in the semiconductor. Now in case of the photoconductivity is an increase in the electrical conductivity of the material that takes place when the material is illuminated with the infrared, visible and ultraviolet light. When falls on the material, then immediately it starts the formation of the transformation of the electron, and we get the conductivity. Now such a type of material becomes more electrically conductive due to the absorption of the electromagnetic radiation, such as visible light or ultraviolet. Any light falls on the material, it absorbs, and energy is increased, and the electrons started to move from one place to another place. Now such a type of N type of and P type of conductors are there. Now these type of conductors, when joined together, then what happens? When we are connected with the electricity in the opposite direction, then electrons are moving towards the P type of conductor, and holes are moving towards the N type of conductor. Now this sometime what happened? These two metals are there, and we found out that there must be some depletion region. It depends on how much voltage is applied. Now the application of this, we can take the PN junction bonding in the field effect transistor. The field effect transistor is an electronic device which uses the electric field to control the flow of current. FET, it is a device where terminals are there, source, gate, and the drain, and where we can control the electricity. Where P type of and N type of junctions are there, N type of FET, P type of FET, and when they are connected, it is classified in terms of the N type of channel, that is PNP junction, and P type of channel, it is a NPN junction. It is used in the amplifier, analog switch, IC, buffers, amplifier, oscillator. In this way, it is a unipolar device. It controls the electric field. We can control the flow of current, and it can be utilized in the number of electronic devices. Now see here, from the source, it is connected to the negative, and PNP, that is the N channel junction is there, and gate where it is connected to the P type of conductor. Then what happens? Electrons are moving very smoothly through the N type of conductor. But when we connect this through the gate, we are increasing the voltage. Then what happens? The depletion zone is increased, and the flow of electron get controlled. And again, if we increase the voltage further, then the depletion region is increased, and flow of current is very, very low. And therefore, this type of transistors can be used to control the voltage as well as to control the current flow. Now in this way, this can be used in the electronic devices. The gallium is a silveric material that can be used in such a type of semiconductors transistors. Gallium arsenide is used in the semiconductor to producing mainly for laser diodes. Light emitting diodes nowadays we are using, and is very familiar with us in the solar panel. It is also used in the creative brilliant mirrors. Gallium arsenide is a very useful compound, oxide monoxide, and it is manufactured for devices such as a microwave frequencies, integrated circuits, monolithic microwave integrated circuits, infrared light emitting diodes, laser diodes, solar cells, etc. in the optical windows. Now such a type of very important things are there, and these are the some questions to evaluate this chapter or this topic, that explain the bonding in solid, define the ion equivalent bond. Now in this way we can evaluate this chapter. We can understand all the answers of these questions. Okay. Thank you.